The universe is not as clear as it seems. Look out at the night sky, and you see a void of perfect black, dotted with sharp, brilliant points of light. It feels like you are gazing through a flawless, infinite window, but that is an illusion. Across the vast gulfs between galaxies, space itself possesses a faint, cosmic fog. This is the Cosmic Opacity Problem, the puzzling fact that the universe is not perfectly transparent to light over immense distances. By the end of this exploration, you will understand the 25 fundamental mysteries that make this simple fact one of cosmology's greatest challenges. Why does light from the farthest quasars appear to vanish, and what does a ghostly forest of absorption lines tell us about the dawn of time? We are about to journey through the layers of this enigma, where each answer reveals a deeper question about the nature of reality itself. What do you believe is hiding in the light we cannot see? The first crack in the perfect window appeared with a strange, distant glow. Across billions of light years, quasars act as the universe's ultimate beacons. These are the violently bright cores of young galaxies, powered by supermassive black holes feasting on matter. Their light is so intense it outshines entire galaxies, piercing the cosmic dark. Astronomers use them as standard candles, predictable lighthouses to measure the vast emptiness between us and them. But when they pointed their telescopes at the most distant quasars, the numbers did not add up. The light arriving at Earth was fainter, significantly fainter, than every model predicted. It was not a problem with the quasars themselves. It was as if something in the immense void was slowly stealing the photons, dimming the beacon before it could reach our eyes. This was the first concrete evidence of cosmic opacity, a tangible fog between the galaxies. The initial reaction was disbelief, a suspicion that the models were wrong or the measurements flawed. Yet, observation after observation confirmed it. The light was being lost. Something out there, spread thinly across the universe, was absorbing or scattering these ancient photons. The hunt for the culprit, for whatever substance could dim a quasar's furious glare, had officially begun. What could possibly be pervasive enough to fill the cosmic voids and yet remain almost invisible to us? The culprit left a fingerprint, a spectral signature written in the missing light. When astronomers broke the faint glow of a distant quasar into its constituent colors, they did not see a smooth rainbow. Instead, they saw a barcode of darkness, a series of sharp, narrow lines where specific colors of light had been completely stripped away. This is the Lyman-alpha forest, and it is the single most important clue in the entire investigation. Each one of those dark lines corresponds to a single, distinct cloud of neutral hydrogen gas floating in the vast intergalactic medium between the quasar and us. As the quasar's light journeys for billions of years, it passes through countless of these clouds. Each cloud acts like a filter, greedily absorbing a very specific shade of ultraviolet light, the wavelength emitted when an electron in a hydrogen atom drops to its lowest energy state. The result is a spectrum scarred by hundreds, sometimes thousands, of these absorption lines, a dense forest of missing light that tells the story of everything the beam passed through. But the forest holds a deeper secret. When scientists compared quasars at different distances, they noticed a startling pattern. The farther away the quasar, and thus the further back in time we are looking, the thicker and denser this forest becomes. The absorption lines crowd together, overlapping, until for the most distant objects, the forest is so thick it becomes an almost continuous blanket of absorption, a phenomenon called the Gunn-Peterson trough. This thickening is the direct, observational proof of cosmic opacity increasing as we look back toward the universe's youth. It tells us that the early universe was a much foggier place, filled with a higher density of this primordial hydrogen gas. The light from the first brilliant objects had to fight its way through a murky soup, and much of it never made it out. So the Lyman-alpha forest is not just a clue, it is a fossil record. Each line is a snapshot of a gas cloud at a specific moment in cosmic history, and the increasing density of the forest paints a clear picture, a universe growing clearer with time as the fog slowly lifts. But this only deepens the central question: what force, what cosmic event, was powerful enough to clear this primordial fog and transform the universe from opaque to transparent? This complete disappearance of the forest is the Gunn-Peterson trough, and it marks a boundary in cosmic history. When astronomers point their telescopes at the very first quasars, the ones whose light has been traveling for over 13 billion years, they see something startling. That entire barcode of dark lines, that intricate forest, is gone. In its place is a single, deep, uninterrupted valley of nothingness. A specific color of ultraviolet light has been almost entirely wiped from the spectrum. This is not because the gas clouds are absent, it is the opposite. The trough tells us that the early universe was so saturated, so utterly packed with neutral hydrogen gas, that there were no gaps left. Every possible path the quasar's light could take was blocked by a hydrogen atom ready to absorb it. Think of it like trying to see a lighthouse through the thickest, densest fog imaginable. The beam is there, but it cannot penetrate the murk. The universe, at this point, was almost perfectly opaque to this crucial wavelength. The Gunn-Peterson trough is the observational proof of a dark age, a time before stars, when the cosmos was a featureless expanse of primordial gas. Yet we are here, looking at it, which means that fog did not last forever. The trough's edge represents the beginning of a cosmic dawn, the moment when something powerful began to rip electrons away from those hydrogen atoms, a process called reionization. This is the epoch of reionization, the universe's great clearing. The challenge is immense. The trough tells us the fog was there, and we know it eventually lifted because we can see the later, clearer universe. But pinpointing exactly when and how this happened is like trying to find the first raindrop in a deluge. What cosmic event was powerful enough to flood the entire universe with enough energy to tear atoms apart? And how did it happen so quickly, in what amounts to a blink of the cosmic eye? This fog between galaxies has a name: the intergalactic medium. It is the loneliest, most diffuse substance in the cosmos, a thin soup of primordial gas that fills the unimaginable voids between the islands of stars. For the longest time, it was considered the closest thing to a perfect vacuum, an afterthought in the grand cosmic story. But when you are dealing with distances measured in billions of light years, even the most tenuous substance becomes significant. This is the heart of the fourth mystery, the opacity of the intergalactic medium itself. What is it, exactly, and how can something so thin cast such a long, faint shadow? The intergalactic medium is mostly hydrogen and helium, the raw materials left over from the Big Bang. It is not uniform. It is a complex cosmic web, with dense filaments of gas tracing the large-scale structure of the universe and vast, almost empty bubbles in between. The gas here is so sparse that by earthly standards it is an ultra-high vacuum, with perhaps only one lonely atom floating in a space the size of a closet. Yet, a beam of light from a distant quasar does not travel through a single closet. It journeys through billions of light years of it. Over such epic distances, the chance of that photon encountering a hydrogen atom, while still incredibly small for any given inch of space, becomes a near certainty. The cumulative effect is a gentle, universe-wide dimming, a faint haze that builds up over the eons. Our models try to map this haze by estimating the density and ionization state of the gas. We know from the Lyman-alpha forest that much of this hydrogen has been ionized, its electrons stripped away by the fierce ultraviolet light from the first stars and galaxies. Ionized hydrogen is transparent. It does not absorb that specific ultraviolet light anymore. So, to match the observed opacity, we have to calculate a precise balance, how much neutral hydrogen remains, how it is clumped into clouds, and how it is distributed along the infinite lines of sight. And here is where the models stumble. When scientists add up everything we think we know, the predicted opacity often does not fully match the deep shadows we actually see in the quasar light. The universe appears just a little bit foggier than our best equations say it should be. This gap suggests we are missing something, perhaps a population of faint, undiscovered gas clouds, or a misunderstanding of how the ultraviolet background radiation that ionizes the gas actually propagates through the cosmic web. The intergalactic medium is not a passive fog. It is an active, dynamic component of the universe, and its subtle opacity is a whisper we are still learning how to hear. But the search for the missing light leads us to a more familiar suspect, one we know all too well from our own cosmic neighborhood: cosmic dust. These are not the fluffy particles in your attic, but microscopic grains of carbon, silicate, and ice, forged in the violent deaths of ancient stars and blown out into space. In our own galaxy, dust is a master of disguise. It scatters blue light more effectively than red, making distant stars appear redder than they truly are, a phenomenon called interstellar reddening. It creates dark, obscuring clouds that blot out entire stellar nurseries. So, a compelling question arises: could this same dust, spread thinly between the galaxies, be the hidden agent of cosmic opacity? Could the faint fog obscuring our view of the earliest quasars simply be a universe-wide haze of interstellar soot? This is the fifth mystery, and it sparks a fierce debate among cosmologists. On one side, the evidence seems suggestive. When astronomers look at the light from some of the most distant quasars, they do see a telltale sign of dust, a subtle reddening. The light appears slightly dimmer and redder than expected, as if it has passed through a faint, diffuse screen. If dust exists in significant quantities in the truly intergalactic void, it would absorb and scatter light across a broad range of wavelengths, not just the specific colors absorbed by hydrogen. This could explain a general, broad, band dimming that simple hydrogen absorption cannot. Proponents of this view point to theoretical models showing how powerful galactic winds from early, frantic star formation could have expelled immense quantities of dust into intergalactic space, seeding the voids with these light-stealing grains. However, the opposing argument is equally strong, and it hinges on a simple problem of supply. To create the level of opacity we observe, you would need a staggering amount of dust, spread uniformly across billions of light years. Dust requires heavy elements like carbon and silicon to form, elements that did not exist in the first few 100 million years after the Big Bang. They had to be cooked up inside the first generations of stars and then blasted out into space. Could this process have been efficient enough and fast enough to pollute the entire cosmos so thoroughly, so early? Many researchers are skeptical. They argue that the observed reddening of quasar light can often be explained by dust within the quasar's own host galaxies, not from a pervasive intergalactic haze. Furthermore, Other precise measurements of the cosmic microwave background, radiation, place very tight limits on how much diffuse dust can exist without leaving an imprint we would have already detected. The debate remains unresolved, a classic scientific standoff. Is the universe's faint opacity due to a ghostly mist of atoms or a fine powder of stardust? The answer may lie not in choosing one, but in understanding how both, in a delicate balance, paint the shadowy portrait of the deep sky. The fingerprint of cosmic fog just grew more complex. Alongside the dominant lines of the hydrogen forest, astronomers spotted something unexpected, a faint secondary set of shadows. These are the metal line systems, and they reveal a universe already contaminated in its youth. In astronomical terms, a metal is any element heavier than hydrogen or helium, the fundamental building blocks forged in the Big Bang. When we see the sharp absorption lines of carbon, silicon, and oxygen in the light of a quasar that shone only 1 billion years after the universe began, it is like finding a sophisticated tool in a prehistoric cave. These elements simply should not exist in such abundance so early. Their creation requires the nuclear furnaces of stars and the cataclysmic explosions of supernova. Therefore, every one of these faint lines is a tombstone, marking the death of a first-generation star. Their presence tells a story of frantic, early enrichment. The first massive stars lived fast and died young, exploding and seeding their surroundings with these newly forged heavy elements, but the mystery deepens with their location. These metal lines are not just found in the spectra of quasars, they are imprinted by clouds far out in the intergalactic medium, in the vast voids between galaxies. This poses a colossal logistical problem. How did these heavy elements, born in the hearts of stars within specific galaxies, get scattered so widely and so uniformly across the cosmos? The force required is almost unimaginable. Galactic winds from those first supernovae must have been titanic, powerful enough to blow entire clouds of metal-enriched gas clear out of their home galaxies and into the cosmic web. This process, called feedback, is like a galaxy polluting its entire neighborhood with the ash of its dead stars. But did it happen quickly enough and efficiently enough to explain the metal lines we see? And more crucially, for our puzzle of missing light, what does this metallic mist do to cosmic opacity? A cloud laced with carbon or silicon absorbs light differently than a simple hydrogen cloud. It can block specific, additional wavelengths. While the total amount of these heavier elements is minuscule compared to the sea of hydrogen, their effect might be disproportionately significant. Could these widely dispersed metallic clouds, this fine dust of dead stars, be contributing an extra layer of haze that our current models of the intergalactic medium fail to fully capture? Each faint line is a clue pointing to a violent, windy, and surprisingly messy cosmic dawn. The universe's fog is not a uniform mist, but a chaotic tapestry of shadow and light. This is the seventh mystery, the profound clumpiness of the intergalactic medium. We have been picturing it as a gentle, all-pervasive haze, but reality is far more intricate. After the Big Bang, gravity sculpted the primordial gas into an immense cosmic web, a spider's silk of dark matter and gas filaments stretching across the emptiness. Where these threads intersect, galaxies cluster like dewdrops. Between them lie the cosmic voids, unimaginably vast regions of near-total nothingness. This structure changes everything about cosmic opacity. A beam of light from a distant quasar is not traveling through a consistent fog. It is on a chaotic obstacle course. For billions of years, It might zip through a relatively clear void, encountering almost nothing. Then, it slams into a dense filament of the cosmic web, a knot of gas 1,000 times thicker than the surrounding space, where it is absorbed and scattered. This means opacity is not a single number for the universe. It is a wildly variable condition depending entirely on your line of sight. Two quasars at the same distance could appear with drastically different brightness, simply because one's light pierced a clearer path through the cosmic voids, while the others journeyed through the dense heart of the web. This clumpiness solves one problem while creating another far greater one. It explains the wide variations we see in quasar spectra, the reason no two forests look exactly alike. But it makes the task of calculating an average, universal opacity a computational nightmare. To predict how much light is lost across the cosmos, you cannot just use a simple average density. You must simulate the entire growth of the cosmic web over billions of years, track the formation of every filament and void, and then shoot millions of simulated light beams through this digital universe to see how many make it through. These are some of the largest, most complex supercomputer simulations ever attempted, digital universes born from equations, and even then, they may not capture the finest, most elusive structures, the tiny, dense clouds that could act as total roadblocks for light. The challenge is to see if the shadows in our real data match the shadows in these simulated ones. So far, the agreement is good, but not perfect. The real universe seems to have a few more dark spots, a few more twists in its web than our best digital twins can yet reproduce. This subtle mismatch whispers that we may still not fully understand the architecture of emptiness itself. Temperature is the silent conductor of this cosmic orchestra. The eighth mystery probes the thermal state of the intergalactic gas itself, because whether that gas is cool and calm or hot and agitated changes everything about how it interacts with light. Think of a hydrogen atom floating in the void. If the surrounding gas is relatively cool, the atom is more likely to hold onto its electron, remaining neutral and ready to absorb that specific ultraviolet light, contributing to the Lyman-alpha forest. But if the gas is hot, the atoms are buzzing with energy, constantly colliding. These violent encounters can rip the electron away, ionizing the atom. An ionized hydrogen atom is transparent to that ultraviolet light. It no longer creates an absorption line. So, the temperature of the intergalactic medium directly controls the balance between neutral and ionized gas, which in turn dictates the opacity of the universe to the most important diagnostic light we have. A few degrees difference in the model can mean the difference between a predicted forest that matches our telescopes and one that is completely wrong. But here is the profound puzzle: we have never directly measured a thermometer out in the cosmic web. We infer the temperature from the very shadows it helps to create, a circular logic that is fraught with uncertainty. We know the gas was not born hot. After the cosmic microwave background radiation faded, the universe entered its dark ages, a time of deepening cold as the expanding cosmos stretched the primordial gas thinner and thinner. Then something happened. A great cosmic heating event began, reheating the intergalactic medium from a few degrees above absolute zero to tens of thousands of degrees. What was the source of this immense energy? The prime suspects are the first luminous objects themselves. The fierce ultraviolet radiation from the earliest stars and galaxies did not just ionize the gas, it also transferred energy, heating it. Quasars, with their unimaginably powerful beams of radiation, could have acted as intergalactic blowtorches, carving out huge, hot bubbles in the cosmic web. Even the shockwaves from collapsing galaxies and exploding supernovae could have pumped thermal energy into the voids. Our models try to piece together this thermal history, a story of heating and cooling that spans billions of years. But did it happen uniformly, or did it create a patchwork of hot and cold zones, with light finding clear paths through some regions and hitting opaque walls in others? If our estimate of the average temperature is off, then our calculation of how much neutral hydrogen remains is also off, leading directly to a flawed prediction of cosmic opacity. The faint haze we measure might not be from extra gas at all, but from gas that is slightly cooler and thus slightly more neutral than we ever expected. Unraveling this thermal mystery requires listening to the most subtle whispers in the light, searching for the faint thermal echo of the universe's first dawn. The universe's great clearing required a staggering energy bill to rip electrons from countless trillions of hydrogen atoms and keep them apart. The cosmos needed a relentless flood of high-energy ultraviolet photons, the specific currency of ionization. Scientists have meticulously calculated this budget, the minimum number of these ionizing photons that must have been produced per second across the entire observable universe to achieve the transparency we see today. Then they turned their telescopes to the cosmic ledger to count every potential source. They tallied the fierce glow of all known quasars. They added the collective ultraviolet output of every young, star-forming galaxy they could see. The numbers were added, compared, and the result was a profound and unsettling shortfall. The account books do not balance. There are simply not enough ionizing photons in the census to pay for the clear universe we inhabit, especially in the critical early epochs when the work of reionization was most intense. This is the ionizing photon budget shortfall, a quantitative mystery that strikes at the heart of our understanding of the cosmic dawn. If our counts are correct, then the known sources of light are insufficient by a factor of 2, perhaps even more. It is as if we walked into a brilliantly lit room, counted every single light bulb, and found their combined wattage could only power a dim nightlight. So where is the hidden power grid? One possibility is that our census is incomplete. Our telescopes, even our most powerful ones, might be missing a vast population of faint, early galaxies, tiny dwarfs that formed stars furiously, but are now too dim to see across such distances. These faint galaxies could be the cosmic equivalents of energy-efficient LED bulbs, numerous and widespread, providing the critical extra photons without being glaringly obvious. Another, more exotic possibility is that the first generations of stars were fundamentally different from the stars we see today. They may have been monstrously large, burning hotter and bluer, producing a far greater proportion of ionizing radiation before exploding. Or perhaps the answer lies not in the stars themselves, but in how their light escaped. In the crowded, gas-rich environments of the first galaxies, most ionizing photons might have been absorbed by local dust and gas before they could even leave their home galaxy. If conditions changed, if galactic winds cleared pathways later on, then the same number of stars could have suddenly flooded the intergalactic medium with a delayed pulse of ionizing radiation, a photon savings account that paid out in one large installment. Solving this budget crisis is essential. Without knowing where the ionizing photons came from, we cannot truly model how the fog lifted, which means our entire picture of cosmic opacity across time rests on an incomplete foundation. The universe's transparency was bought with a currency we have not yet fully accounted for. Our search for the missing photons leads us to the smallest, faintest building blocks of the cosmos. If the brilliant quasars and majestic spiral galaxies cannot provide enough ionizing power, perhaps the answer lies in the multitudes, in a cosmic population we have barely begun to see. This is the faint galaxy problem, the tantalizing possibility that the early universe was teeming with countless tiny, dwarf galaxies, each one a faint but prolific producer of the ultraviolet light needed to clear the fog. These galaxies would be the unsung heroes of reionization, their collective output far outweighing the contribution of the rare, brilliant beacons. The logic is compelling. In the modern universe, small dwarf galaxies outnumber large ones by a huge margin. It stands to reason that in the infant cosmos, the first structures to light up were also the smallest, fragile clumps of gas and dark matter just beginning to spark with their first stars. But there is a profound observational challenge. These galaxies are, by definition, extremely faint. Their light is stretched and dimmed by the expansion of the universe to an almost imperceptible whisper. For decades, our telescopes simply lacked the sensitivity to see them in any significant numbers. It was like trying to count fireflies from a mile away with a pair of binoculars. You might catch a glimpse of the brightest few, but the true swarm remained hidden in the dark. This created a glaring gap in our cosmic census, a missing chapter in the story of the first light. If these galaxies existed in the vast numbers required, they could easily solve the ionizing photon budget shortfall. A trillion faint embers can produce as much heat as a single roaring bonfire. The question shifted from theory to a direct, technological hunt. Could we finally see this hidden population? The arrival of the James Webb Space Telescope promised a revolution. With its enormous, cold mirror and infrared eyes, Webb was built to see these first glimmers. It can peer back to the era of reionization and detect galaxies hundreds of times fainter than anything Hubble could see. The early results have been breathtaking, revealing a universe that looks far more crowded and active in its youth than we ever imagined. Galaxy after tiny galaxy has appeared in Webb's deep field images, many that are little more than faint smudges of light. This seems like the solution we have been waiting for. Yet, the mystery has not been solved, it has merely deepened. As astronomers meticulously count these newfound faint galaxies and calculate their total ultraviolet output, a worrying trend is emerging. Even with Webb's phenomenal vision, the numbers are still not quite adding up. The galaxies are there, but there may not be enough of them, or they may not be producing ionizing photons as efficiently as our models hoped. It is as if we finally got a powerful telescope to count the fireflies, and while we see more than before, the swarm is still not dense enough to explain the brilliant glow on the horizon. This leaves us at a fascinating crossroads. Either these faint galaxies are even more numerous and fainter than Webb can currently detect, hiding just beyond the edge of its vision, or our understanding of how stars produce and release ionizing radiation in the early universe is fundamentally flawed. Perhaps the first stars in these small galaxies were uniquely potent, or perhaps the galaxies themselves were leakier, allowing more of their hard ultraviolet light to escape into intergalactic space. The faint galaxy problem has evolved from a hopeful hypothesis into a precise observational test, one that is currently underway. With every new deep field image, Webb is not just showing us the first galaxies, it is auditing the universe's energy budget during its most critical transformation. The answer will determine whether we have finally found the architects of transparency, or if we must look for an even more exotic source of power, even if every galaxy blazed with the necessary ultraviolet fire, a second, more subtle barrier stood in the way. This is the escape fraction enigma, a simple question with a universe-altering answer. What percentage of those vital, ionizing photons actually manages to break free from their home galaxy? A galaxy is not a bare light bulb in a vacuum. It is a swirling, chaotic maelstrom of gas, dust, and newborn stars. The very stellar nurseries that produce the hard ultraviolet light are embedded in thick clouds of the raw material they formed from. Before a photon can even begin its multi-billion-year journey to clear the cosmic fog, it must first run a brutal local gauntlet. It can be absorbed by a nearby hydrogen atom, reionizing it right back to neutral, a process that does nothing for the wider universe. It can be scattered by a grain of dust, redirected into oblivion. The escape fraction is the slim minority that makes it out, punching through the galaxy's gaseous halo into the freedom of intergalactic space. This number is arguably the single greatest unknown in the entire reionization puzzle. Think of it this way: if the escape fraction is only 5%, then galaxies must produce 20 times more ionizing photons internally just to get the same amount into the intergalactic medium as they would if the escape fraction were 100%. Our entire photon budget calculation collapses if we do not know this one critical value. The problem is, measuring it directly is fiendishly difficult. We cannot simply point a telescope at a distant galaxy and count the ionizing photons streaming out, because any intergalactic hydrogen between us and that galaxy will have already absorbed them, creating the very Lyman-alpha forest we study. It is a cosmic catch-22. The signal we need to measure is the one that gets completely erased by the process we are trying to understand. Astronomers must use ingenious, indirect methods. They look for telltale signatures in the light that does escape, like the specific colors of helium emission, which can hint at how much ionizing radiation is present. They create incredibly detailed computer models of galaxies, simulating the chaotic paths of millions of photons as they bounce through virtual clouds of gas. The results from these methods are all over the map. Some studies of nearby galaxies, which we can examine in fine detail, suggest escape fractions of just a few percent. Others, looking at different types of galaxies or using different theoretical models, suggest it could be 10, 20, or even 50% in the early, more compact galaxies. This is not a minor disagreement, it is a chasm. A factor of 10 uncertainty in this one parameter means our understanding of the cosmic dawn could be off by an entire order of magnitude. Did the first galaxies have to be unimaginable powerhouses, or were they merely moderately bright but exceptionally leaky? The opacity of the entire universe may hinge on the answer to how well a single galaxy can hold onto its most precious light. The very galaxies that light the cosmos can also be its greatest veils. While we have been searching the voids for a diffuse haze, some of the most profound opacity comes from the galaxies themselves, acting as colossal, drifting clouds that block the light from anything behind them. This is not about the faint intergalactic mist, but about running headlong into a nearly solid wall of gas and dust. When the light from a distant quasar passes directly through the outer halo or disk of a foreground galaxy, something dramatic happens. Astronomers see it in the spectrum as a damped Lyman-alpha system. The name tells the story, damped. Unlike the sharp, narrow lines of the forest, the absorption line here is broad and deep, almost black. It indicates a column of hydrogen so incredibly dense. It is like the gas found within a modern galaxy's disk. This is not a wispy intergalactic cloud. This is the raw, cold fuel of star formation itself, a galactic building block caught in the act. These systems absorb virtually all the Lyman-alpha light at that wavelength, creating a total roadblock for those specific photons, but they do more than that. The sheer density of gas means it also absorbs light at shorter, even more energetic wavelengths. When the column density becomes high enough, we cross into another regime, the Lyman limit system. Here, the gas becomes so thick it acts like a solid filter, absorbing not just a specific color, but all ultraviolet light with wavelengths shorter than a specific cutoff point, the Lyman limit. It is the difference between a colored filter and a brick wall. A quasar shining behind such a system would have its entire ultraviolet blaze, its most important diagnostic light, completely extinguished before it even begins its long journey through the intergalactic forest. This presents a monumental mapping challenge. To understand the total cosmic opacity, we must account for these galactic roadblocks. How many of them are out there? What fraction of the sky is covered by the cross-sectional area of galaxy halos and disks across cosmic time? Imagine trying to predict how often a distant streetlight will be obscured by drifting fog banks, but where the fog banks are themselves entire cities, and they grow and change over billions of years. Young, gas-rich galaxies in the early universe likely had much larger gaseous envelopes, making them bigger targets. As galaxies age and use up or expel their gas, their effective cross-section for absorption shrinks. So the opacity contributed by galaxies themselves is not constant, it evolves dramatically. Pinpointing this evolution is critical. If we underestimate how many quasars are hidden behind these damped systems, especially in the early universe, we are not getting a true census of the light sources themselves, which skews all our other measurements. Each of these dense absorbers is a galaxy caught in silhouette, a dark fingerprint against the brilliant light of the cosmic dawn, reminding us that to see the deepest universe, we must first peer through the tangled structures of its inhabitants. The universe is bathed in a faint, forgotten afterglow. Beyond the sharp light of stars and quasars, there exists a diffuse sea of ultraviolet radiation, a cosmic hum left over from the dawn of time. This is the cosmic ultraviolet background, and it is the master regulator of the intergalactic medium. Every ionizing photon that escaped a galaxy, every blazing quasar beam, contributed to this all-pervasive bath of energy. Its role is critical. It is what keeps the fog from reforming. Imagine it as a universal disinfectant light, constantly shining on the hydrogen atoms in the voids. If an electron manages to recombine with a proton to form a neutral atom, this background radiation is there to immediately rip it apart again. It maintains the ionization balance, holding the universe in its transparent state. This creates a profound feedback loop. The opacity of the intergalactic medium depends on how many neutral atoms exist, which depends on the intensity of the ultraviolet background, which itself depends on the opacity, because that same fog can absorb the very radiation trying to clear it. It is a cosmic equilibrium, a delicate dance between light and shadow. The central mystery is that we have never directly measured this background with precision. We cannot simply point a telescope at an empty patch of sky and measure its ultraviolet glow, because our own galaxy's atmosphere and interstellar dust scatter light, creating a foreground haze that drowns out the faint cosmic signal. It is like trying to hear a whisper in a crowded, noisy room. Instead, astronomers must use incredibly clever, indirect probes. They study the shadows. By examining the fine details of the Lyman-alpha forest, how sharp or blurred the absorption lines are, scientists can back-calculate the intensity of the ultraviolet radiation that must have been shining on those clouds to produce the exact ionization state we see. It is detective work of the highest order, inferring the properties of the light by studying the shadows it casts. The problem is, different methods yield different answers. Measurements from one line of sight suggest a certain intensity, while data from another quasar suggests something slightly different. Is the background uniform or patchy? Does its spectrum, the mix of different ultraviolet colors, match what we expect from known sources like quasars and galaxies? An error in our estimate of this background is not a minor detail. It propagates directly into a fundamental error in our model of cosmic opacity. If we think the background is stronger than it truly is, we will model the intergalactic medium as being more ionized and thus more transparent than it actually is. This would force us to invent extra sources of opacity, like mysterious dust or unknown gas clouds, to explain the deep shadows we observe. Conversely, if we underestimate the background, we would overestimate the amount of neutral hydrogen, making our opacity models too pessimistic. The cosmic ultraviolet background is the silent conductor of this entire symphony, and we are still trying to discern its true volume from the distant echoes of the music it creates. Hydrogen may be the star of the cosmic opacity story, but it is not the only actor on the stage. For every 10 atoms of hydrogen in the universe, there is about 1 atom of helium, the second element forged in the fiery minutes after the Big Bang. This brings us to a deeper, more energetic chapter in the story of cosmic fog, the helium reionization puzzle. While hydrogen's electron is relatively easy to strip away, helium puts up a much tougher fight. To remove the first electron from a helium atom requires an ultraviolet photon with more than twice the energy of a hydrogen ionizing photon. To fully strip both electrons and create doubly ionized helium requires a staggering 24 times more energy, placing it firmly in the realm of extreme ultraviolet and even soft X-ray radiation. The sources for this kind of power are far rarer. Normal stars, even the hottest, youngest ones, cannot produce enough of this hard radiation. The prime suspects are quasars, the most energetic engines in the cosmos, whose blazing cores emit a torrent of high-energy photons capable of tearing into helium's strong grip. This leads to a fascinating and delayed cosmic event. Evidence written in the spectra of distant quasars suggests that while hydrogen reionization was largely complete by the time the universe was about 1 billion years old, helium had to wait. A second, later epoch of reionization likely occurred, a separate wave of cosmic clearing that swept through the universe when quasars became more common, perhaps 2 to 3 billion years after the Big Bang. The mystery is not just when it happened, but how it unfolded and what it did to the cosmic landscape. This helium reionization would have injected a tremendous amount of heat into the intergalactic medium, potentially reheating the gas by tens of thousands of degrees. Hotter gas expands, changing the delicate pressure balance within the filaments of the cosmic web. This could have altered the distribution of gas, puffing up some clouds and dissipating others, thereby changing the very architecture of the Lyman-alpha forest. For a time, it might have even made the universe slightly more opaque, as the heated, expanding gas created a more complex and turbulent barrier for light. So the universe's journey to transparency was not a single, smooth transition from dark to light. It was a layered process, with hydrogen clearing first in a fog lit by the first stars and galaxies, followed by a later, more violent clearing of helium by the brilliant, piercing light of quasars. Each element has its own timeline, its own energy requirement, and its own effect on the overall opacity we measure today. To truly understand the faint haze between the galaxies, we must now listen for the echoes of two separate dawns. The cosmic web is threaded with a ghost of unimaginable heat. Between the cool, neutral clouds of the Lyman-alpha forest lies a second, hidden ocean of matter, a plasma so hot it glows not in visible light, but in the fierce energy of X-rays. This is the warm, hot intergalactic medium, or WIM, a theorized component of the cosmic web that has been heated to temperatures of millions of degrees. For decades, it existed only in supercomputer simulations, a prediction of where the other half of the universe's normal matter might be hiding. You see, when astronomers tally all the stars, galaxies, and cool gas we can see, they come up short, finding only about half of the ordinary matter, the protons and neutrons, that the Big Bang should have produced. The WIM is the prime suspect for this missing baryon problem, a diffuse, searing plasma hiding in the filaments connecting galaxy clusters, but its discovery creates a profound new wrinkle in our opacity puzzle. This gas is in a state of near total ionization. The fierce heat has stripped atoms not just of one electron, but of many, leaving behind bare atomic nuclei and free-flying electrons. This means it is utterly transparent to the ultraviolet light that defines the Lyman-alpha forest. A hydrogen atom needs its electron to absorb that specific color, and here, the electrons are long gone. So, if the WIM is invisible to our primary tool, how could it possibly contribute to cosmic opacity? The answer requires us to look at a different kind of light. This superheated plasma interacts powerfully with high-energy photons, particularly X-rays. The free electrons in the WIM can scatter X-ray photons, a process called Compton scattering, subtly redirecting them and creating a faint, diffuse haze in the X-ray sky. Furthermore, the highly ionized atoms, like oxygen stripped of 7 of its 8 electrons, can absorb very specific, high-energy X-ray wavelengths, creating their own faint forest of absorption lines, but in a part of the spectrum far harder to observe. The mystery is one of balance and distribution. If the WIM is as widespread and massive as theorists believe, woven through the cosmic web, then its cumulative effect on X-rays traveling across the universe could be significant. It would mean the cosmos has not one, but two overlapping veils, a cool ultraviolet fog from neutral hydrogen and a shimmering, hot X-ray haze from the WIM. The challenge is that observing this directly is at the very edge of our capability. Detecting the WIM requires incredibly sensitive X-ray telescopes and the luck of having a brilliant, distant X-ray source, like a quasar, shining right through a dense filament of this hot plasma. A handful of tentative detections have been made, whispers of highly ionized oxygen absorption in X-ray spectra, but a full map remains elusive, so we are left with a tantalizing possibility that a major component of the universe's ordinary matter is also a source of opacity we have barely begun to measure. Its contribution is not in dimming the starlight we see with our eyes, but in subtly filtering the universe's most energetic screams, a hidden thermal curtain drawn across the deepest voids. The most brilliant beacons in the cosmos are also its most complex shadows. Active galactic nuclei, the hyperactive hearts of galaxies powered by supermassive black holes, present a profound paradox in the story of cosmic opacity. On one hand, they are the universe's ultimate floodlights. The quasar phase of an active galactic nucleus unleashes a torrent of radiation across the entire spectrum, from radio waves to gamma rays, with a ferocious intensity that can outshine its host galaxy 1,000 times over. This radiation, especially its high-energy ultraviolet and X-ray component, is the most effective tool imaginable for clearing fog. It can ionize hydrogen and helium far beyond its own galaxy, carving out vast, transparent bubbles in the intergalactic medium that can be millions of light-years across. In many ways, an active galactic nucleus is a cosmic vacuum cleaner, blasting away the obscuring gas in its vicinity and creating highways for light. But this is only half the story. To fuel this incredible brilliance, matter must fall toward the black hole at the galaxy's center. This material does not fall in cleanly. It forms a swirling, superheated accretion disk and is often funneled into powerful jets. Crucially, this entire engine is shrouded in a dense, chaotic structure called the torus, a thick donut of gas and dust on a colossal scale. From certain angles, this torus completely obscures our view of the brilliant core, blocking its light entirely. Even when we see the quasar shining directly, the light must first escape this incredibly dense, local environment, a gauntlet of absorption that can imprint its own deep, complex shadows on the spectrum. So an active galactic nucleus is both a piercing searchlight and a massive, drifting fog bank, all at once. This duality creates a monumental accounting problem for cosmologists. Over the lifetime of the universe, as active galactic nuclei flicker on and off, what is their net effect on the cosmic opacity budget? Do they, on average, clear more fog than they create? The answer is not simple because it changes over cosmic time. In the early universe, quasars were rarer but might have been more important for the final stages of reionization, particularly for helium. Later on, as they became more common, their collective effect on heating and ionizing the intergalactic medium would have been significant, but so too would the total cross-sectional area of their obscuring tori, potentially blocking the light from background sources. Quantifying this requires knowing not just how many active galactic nuclei existed, but for how long each one was active, how much gas was in its torus, and from what angles its light was beamed. It is a four-dimensional puzzle of time, orientation, and power. We are left with a cosmic balance sheet where the entries are written in both light and shadow, and the final total for these magnificent engines remains one of the great unsolved calculations in the story of the universal haze. This cosmic history of light and shadow has a shape, a curve that charts the universe's journey from blindness to sight. We can now attempt to synthesize the timeline, to draw the graph of cosmic opacity from the Big Bang to the present day. At the very beginning, in the first 380,000 years, the universe was a searing plasma, a perfect fog. Opacity was effectively infinite, as photons could not travel more than a tiny fraction of an inch before scattering off a free electron. This is the era captured in the cosmic microwave background, the moment the fog lifted just enough for the first flash of light to escape. Then came the Dark Ages, a period of profound stillness. As the universe expanded and cooled, protons and electrons combined to form neutral hydrogen and helium. The plasma fog cleared, but a new, deeper fog set in, a cold, neutral murk. Opacity to ultraviolet light was near total, a perfect Gunn-Peterson trough across the entire sky. The curve on our graph here is a flat line at maximum darkness. The transformation began with cosmic dawn. The first stars and galaxies flickered on, and their fierce ultraviolet radiation started to eat away at the fog, creating ever-growing bubbles of clarity. This is the epoch of reionization, a dramatic plunge in the opacity curve as the universe shifted from neutral to ionized. By roughly 1 billion years after the Big Bang, the curve likely reached a minimum, a point of greatest transparency. The primordial hydrogen was largely ionized, the cosmic web was still diffuse, and large amounts of dust had not yet been produced and expelled. The universe was, for a fleeting moment, a relatively clear window. But the story does not end with a simple, clear universe forever after. Here lies the profound mystery of the curve's later shape. As cosmic evolution continued, galaxies grew, merged, and filled with stars. Those stars forged heavy elements and, in their deaths, created dust. Powerful galactic winds then blew this dust, along with clouds of gas, out into intergalactic space. The formation of massive galaxy clusters created vast reservoirs of hot gas, the warm-hot intergalactic medium. The later epoch of helium reionization by quasars injected new heat and turbulence. Each of these events could have nudged the opacity curve back upward. Did the universe, after reaching a transparency minimum, slowly grow foggier again? Not with a primordial hydrogen fog, but with a more complex haze of metals, dust, and hot plasma. The shape of this curve is one of cosmology's great unsolved puzzles, because our data points are heartbreakingly sparse. We have a solid point at the beginning from the cosmic microwave background. We have a few incredibly difficult to interpret points during reionization from the handful of ultra-distant quasars and galaxies we can find. We have a somewhat better understanding of opacity in the recent, nearby universe, but the detailed trajectory, the precise slope of the rise and fall, is like trying to map a mountain range with only 3 or 4 points of elevation. Different theoretical models produce wildly different curves, some showing a gentle rise after reionization, others a sharper increase, and some even suggesting a complex series of peaks and valleys as different processes dominated. Until we can find more beacons, more standard candles shining from different cosmic epochs, the true history of the universal veil will remain a sketch, a ghostly line waiting to be drawn in solid ink. Our story of cosmic fog now collides with the universe's oldest photograph. To truly test our understanding of opacity, we must consult an independent witness, one that saw the cosmos when it was a mere infant. This is the cosmic microwave background radiation, the faint, cold glow that fills every corner of the sky. It is the afterglow of the Big Bang itself, released when the universe was only 380,000 years old, the moment it first became transparent to light. Embedded in this ancient snapshot is a subtle, crucial clue about everything that happened afterward, specifically, the epoch of reionization. As the first stars and galaxies flooded the universe with ultraviolet light, they did not just ionize hydrogen for the first time, they created a sea of free electrons all over again. These newly liberated particles left a unique fingerprint on the cosmic microwave background. When the CMB photons, on their 13 billion-year journey to our telescopes, passed through these clouds of free electrons, a tiny fraction of them scattered. This scattering imprinted a specific pattern, a faint polarization signal, on the microwave light. By measuring this signal with exquisite precision, satellites like Planck can essentially count the total number of free electrons created across cosmic history. From that number, scientists can deduce the timing and duration of the reionization process. It is a completely independent cosmic audit, a check written not from starlight, but from the universe's own primordial glow. And here, a quiet but persistent mystery emerges. The story told by the cosmic microwave background does not perfectly match the story written in the missing light of quasars. The CMB data suggests reionization was a relatively late and rapid event, beginning sharply and concluding by the time the universe was around 1 billion years old. However, the evidence from the most distant quasars and their Gunn-Peterson troughs hints at a more gradual, perhaps earlier beginning. Some quasar spectra suggest patches of the universe were already significantly ionized earlier than the CMB prefers. This is not a glaring contradiction, but a subtle tension, a slight misalignment in the cosmic clocks. It suggests a gap in our understanding. Perhaps the process was more complex and patchy than our smooth models assume. Maybe the sources of ionizing photons were distributed unevenly, creating early bubbles of clarity in an otherwise neutral sea, which the quasars see, while the CMB measures only the global, average effect. Alternatively, could there be unknown physics affecting how the CMB photons scatter, or an incomplete understanding of how to interpret the quasar absorption forests? This tension is precisely what drives science forward. It tells us that our two best windows into the cosmic dawn, one looking at ancient shadows and one measuring an ancient glow, are seeing slightly different facets of the same truth. Resolving this discrepancy will force us to refine our picture, to find the missing piece that makes both stories align, revealing whether the universe cleared its throat in a sudden shout or a drawn-out, stuttering sigh. Gravity's invisible hand sculpts the entire stage for this drama of light and shadow. To truly grasp cosmic opacity, we must now venture into the most profound and speculative layer of the mystery, the role of the universe's dark components. First, consider dark matter. This enigmatic substance does not emit, absorb, or scatter light. It is perfectly transparent to photons, yet its gravitational influence is the master architect of the cosmic web. Every filament, every cluster, every vast void is defined by the underlying scaffold of dark matter. Ordinary gas, the stuff that actually absorbs light, simply flows into the gravitational wells that dark matter creates. This means the distribution of the absorbing gas, the density of the Lyman-alpha forest, and the location of every damped system are all direct consequences of the dark matter model we use. If our understanding of dark matter is even slightly flawed, if it clumps differently or interacts in subtle ways we have not anticipated, then our entire map of the cosmic web is wrong. Our predictions for how gas is distributed along a quasar's line of sight would be based on a faulty blueprint, leading directly to incorrect calculations of cosmic opacity. Could a hidden property of dark matter be the reason our simulated shadows do not perfectly match the real ones? Then there is dark energy, the even more mysterious force accelerating the expansion of the universe. This acceleration is not a minor detail. It is the dominant factor governing the cosmic stage over the last several billion years. Dark energy controls the expansion rate, which in turn dictates the path length a photon must travel from a distant quasar to our telescopes. Think of it as setting the total distance of the obstacle course. If the expansion history were different, if the universe expanded faster or slower in the past, then light would have spent more or less time journeying through the absorbing medium. A longer path means more opportunities to encounter absorbing clouds, accumulating a thicker haze. A shorter path means less. Our entire interpretation of opacity measurements hinges on our precise model of this expansion history, a model built on the assumption that dark energy behaves as a simple cosmological constant. But what if it does not? What if dark energy's strength has varied over time? A different expansion history would stretch or compress our timeline of events like reionization, change the density of the intergalactic medium at every epoch, and ultimately alter the total amount of fog we expect light to pass through. These are not minor adjustments, they are foundational. We are trying to measure a faint haze by looking across an abyss whose very size and shape are dictated by forces we cannot see. The opacity of the universe may be the final, subtle clue that helps us understand the darkness itself. Every shadow we have studied is filtered through the lens of our own technology. The 20th mystery forces us to confront a humbling reality, that the cosmic opacity problem is entangled with the technological limits of observation itself. Our entire understanding of this universal haze is built upon a chain of measurements so delicate, so demanding, they push our greatest instruments to their absolute breaking point. The first and most fundamental challenge is the sheer faintness of the signal. To detect the Lyman-alpha forest, we need a brilliant, distant quasar shining behind billions of light-years of absorbing gas. But such quasars are incredibly rare, cosmic lighthouses separated by vast, dark oceans. Finding them is a needle in a haystack search across the entire sky. Even when we find one, its light arrives as a ghostly whisper, having been stretched by cosmic expansion into the near-infrared and dimmed to a billionth of its original intensity. Capturing that whisper requires not just a large telescope, but an exquisitely sensitive spectrograph, an instrument that can split that faint light into a rainbow of thousands of individual colors to read the barcode of absorption lines. Every step in this process introduces noise, a statistical fuzz that can hide the very features we seek or create false signals that mimic them. Then there is Earth's own veil, our atmosphere. It churns and blurs, scattering light and absorbing specific infrared wavelengths where the most distant quasars shine brightest. Ground-based telescopes must use complex adaptive optics to correct for this shimmering, and even then, they miss crucial pieces of the spectrum. For decades, these limitations meant we only had clear spectra for a few dozen of the most luminous quasars, a tiny, possibly biased sample of the universe. The central question becomes haunting: to what degree are the puzzles we have outlined, the budget shortfalls and timeline tensions, simply artifacts of our imperfect view? Could a clearer, more complete dataset make these mysteries vanish? This is where the revolution begins. The James Webb Space Telescope, operating in the cold, stable silence beyond our atmosphere, is built to shatter these limits. Its infrared eyes are sensitive enough to see fainter quasars and galaxies than ever before, expanding our sample from a handful of beacons to a crowd. Its pristine spectra are free from atmospheric contamination, revealing the forest of absorption lines with a clarity that feels almost shocking. With Webb, we are no longer squinting at a faded, torn manuscript. We are beginning to read the cosmic ledger in high definition. The mystery is whether this new clarity will resolve our questions or deepen them, revealing subtler shadows and more complex patterns in the universal fog that our old, blurry instruments could never have glimpsed. To test our theories against the faint whispers of the cosmos, we must first build a universe from scratch. This is the 21st mystery, a world born not from fire and gravity, but from silicon and electricity. In supercomputer facilities around the globe, cosmologists perform a kind of digital alchemy. They start with the initial conditions of the Big Bang, a near-uniform soup of dark matter and primordial gas, and then let the laws of physics play out over billions of simulated years. These are not simple animations. They are staggeringly complex calculations that track the gravitational dance of trillions of particles, the hydrodynamics of gas flowing and cooling, and the explosive feedback from stars and black holes. The goal is to create a virtual cosmos that, when we look at it, matches the one we see outside our telescopes. From this digital universe, we can then shoot simulated beams of light from simulated quasars and measure the exact opacity our models predict, creating a perfect test for our ideas. Yet, there is a fundamental and fascinating flaw at the heart of this grand endeavor, known as the problem of subgrid physics, a simulation that tracks every atom in the observable universe is impossible, even for the most powerful supercomputers. So, the models must work at a scale. They simulate the large cosmic web by breaking it into enormous chunks, or cells, that can be hundreds or even thousands of light years across. Within each of these vast cells, unimaginably complex, small-scale processes are happening, processes that ultimately shape the cosmic story. A single star being born in a dense cloud, the shockwave from a supernova tearing through interstellar gas, the delicate balance of heating and cooling in a galactic disk. These events occur on scales far smaller than the simulation's resolution. They are happening, in essence, inside the grid. Since the computer cannot calculate them directly, scientists must invent approximate recipes, educated guesses packaged into equations, that describe the average effect these tiny processes have on the giant cell. This is subgrid physics, a set of rules for the unseen. For example, a simulation might have a rule that says, if the gas in a cell reaches a certain density and temperature, then 10% of it will be turned into stars over a certain time, and those stars will inject a specific amount of energy back into the cell. These rules are based on our best understanding, but they are still guesses, and here is where the mystery for cosmic opacity becomes so delicate. The formation of stars directly controls the production of ionizing photons that clear the fog. The expulsion of gas and dust from those stars seeds the intergalactic medium with the very material that can reabsorb light. If the subgrid recipe for star formation is off by just a small amount, if stars form a little too efficiently or not efficiently enough, the entire history of reionization in the simulation shifts. A slight overestimate in the energy from supernovae might blow too much gas out of galaxies too early, creating a different pattern of absorbing clouds in the cosmic web. These tiny errors in the recipe for the unseen do not cancel out, they cascade. Over billions of simulated years, they amplify, leading to a predicted universe that might be too transparent or too opaque compared to our own. The haunting question for every cosmologist is this: are the shadows we see in the real day evidence of new physics, or are they simply the ghostly imprint of our own imperfect approximations, a reminder that we have not yet found the perfect recipe for a star? The recipes for our digital universes are built on a foundation of unshakable laws. We assume the physics governing light and atoms today operated exactly the same way 13 billion years ago and 10 billion light years away. But what if that foundation itself is shifting? This leads us to the 22nd mystery, a realm of truly radical alternatives where the dimming of distant light might not be caused by a cosmic fog at all, but by a fundamental change in the rules of reality. The most famous of these fringe ideas is the tired light hypothesis, proposed nearly a century ago as an alternative to the expanding universe. It suggests that photons simply grow weary on their long journey. Instead of the redshift of light being caused by the stretching of space itself, tired light proposes that photons gradually lose energy through interactions with a mysterious medium or some unknown process, making them redder and dimmer over vast distances. In this view, a quasar looks faint not because its light was absorbed by intervening gas, but because the photons themselves ran out of steam. While elegantly simple, this hypothesis has been overwhelmingly rejected by modern cosmology. The evidence against it is decisive. We observe specific effects, like time dilation in the light curves of distant supernova, that can only be explained by an expanding universe, not by tired light. The cosmic microwave background's precise blackbody spectrum is another fatal blow. If photons were constantly losing energy through random interactions, that perfect thermal signature would be scrambled. So tired light remains a historical footnote, a dead end in our understanding, yet it opens the door to a more serious, if still highly speculative, line of inquiry. Could the fundamental constants of nature themselves be changing over cosmic time? Consider the fine structure constant, a magical number that governs the strength of the electromagnetic force. It controls how tightly electrons are bound to their atomic nuclei. If this constant were slightly different in the distant past, it would change the very signature of atoms. The specific wavelength of light a hydrogen atom absorbs, the one that creates the entire Lyman-alpha forest, would shift. A smaller constant might mean absorption happens at a slightly bluer color, a larger constant at a slightly redder one. If this constant has been slowly drifting over billions of years, then the forest of lines we see in a quasar spectrum is not a perfect map of gas clouds at fixed energies, but a subtly distorted one. This could, in principle, mimic some effects of opacity or alter our interpretation of how much gas is truly there. A handful of controversial studies over the years have claimed to detect such a variation by comparing quasar absorption lines from different eras, though these results are hotly debated and far from confirmed. The vast majority of evidence suggests the constants are, in fact, constant, but the mere possibility lingers on the extreme frontier of physics, a ghost in the machine. It forces a profound question: is the universe's apparent haze a real substance, or could it be an illusion created by the slow, subtle evolution of the laws of physics themselves? While the answer almost certainly points to a real, material fog, the question reminds us that in cosmology, even our most basic assumptions must occasionally be held up to the light. The universe's expansion rate is not just a number, it is the clock that times every event in cosmic history. A profound and unresolved disagreement over the precise value of this rate, known as the Hubble tension, is currently shaking the foundations of cosmology. On one side, meticulous measurements of the cosmic microwave background radiation, the universe's baby picture, give us one very precise speed for the expansion. On the other side, observations of stars and supernova in the nearby, modern universe give us a significantly faster speed. The two most trusted methods in all of science are telling us two different stories about how fast the cosmos is growing. This is not a small statistical fluke. It is a glaring discrepancy that suggests something fundamental is missing from our standard model. To resolve it, theorists are exploring dramatic revisions to early universe physics. Perhaps dark energy is not constant, but evolved. Maybe a new, exotic form of radiation flooded the early cosmos. Or perhaps the universe experienced a brief, violent phase change moments after the Big Bang. Each of these proposed fixes does not just tweak the expansion rate. It rewinds the cosmic clock and changes the conditions during the epoch of reionization. Think of it like adjusting the starting temperature and pressure in a recipe. The entire cooking process and the final texture of the cake will be different. If the early universe expanded faster or slower than we thought, then the timeline for the formation of the first stars and galaxies shifts. A faster early expansion would mean matter was more spread out, making it harder for gravity to pull together the first luminous structures. This could delay reionization, leaving the universe shrouded in neutral hydrogen fog for longer. Conversely, a slower early expansion might accelerate structure formation, causing stars to ignite earlier and clear the fog more quickly. This creates a direct and tantalizing link between two of cosmology's greatest puzzles. The cosmic opacity we measure from the shadows in quasar light is a direct fossil of that reionization timeline. Therefore, the opacity data acts as an independent referee. Any new physics proposed to solve the Hubble tension must also correctly predict the opacity we actually observe. It is a cosmic cross-check. Could the faint haze between galaxies hold the key to calibrating the universe's expansion, or will a solution to the Hubble tension finally provide the correct blueprint for how the first light pierced the darkness? These two mysteries are now intertwined, each one holding a piece of the other's solution, waiting for the moment when a single elegant idea makes both shadows and speeds align. Beyond the brilliant but steady glow of quasars, the cosmos holds a more violent and fleeting kind of beacon. For a few precious seconds, a gamma-ray burst can outshine every other source of light in the universe, releasing more energy than our Sun will in its entire 10 billion-year lifetime. These catastrophic explosions, likely signaling the birth of a black hole from a collapsing massive star or the merger of neutron stars, are the most luminous events since the Big Bang itself. Their staggering brightness is not just a spectacle, it is a promise. Because they are so intensely brilliant, we can see them from much, much farther away than even the most distant quasar. A gamma-ray bursts afterglow, shining across X-ray, optical, and radio wavelengths, can act as a flashlight powerful enough to illuminate the cosmic fog all the way back to the universe's very first few 100 million years, to an era before the first quasars ever switched on. This is the future of cosmic opacity research, and it presents a thrilling mystery. What will we see when we finally shine this new, more powerful beam into the deepest shadows? The light from these ancient bursts must travel through the primordial intergalactic medium during the epoch of reionization's earliest, most chaotic phases. By analyzing their spectra with the same techniques used on quasars, we will be able to map the density and ionization state of the gas with unprecedented precision, tracing the very first bubbles of clarity as they formed. The mystery is whether this new data will simply confirm the story we have pieced together from quasars, filling in missing details, or if it will shock us by revealing an entirely new chapter. Perhaps the early universe was even foggier than our most pessimistic models suggest, filled with a previously unknown population of cold, dense gas clouds that completely block our view. Or perhaps, against all odds, we will find patches of surprising transparency earlier than anyone thought possible, hinting at the existence of fantastically powerful and early sources of light we have not yet dreamed of. Each detected gamma-ray burst from the cosmic dawn is like turning on a searchlight in a cavern we have only ever mapped by listening to echoes. We do not yet know if the walls will be where we predicted, or if we will find ourselves standing in a chamber vaster and stranger than we ever imagined. The next great revelation about the universal veil may be written in a flash of light so fierce it died before our planet was even born. This final mystery is not about a shadow in the data, but about the nature of the shadow itself. The Cosmic Opacity Problem, in all its 24 layers, presents us with a humbling truth. There is a fundamental, physical limit to what we can see. No matter how powerful our telescopes become, no matter how clever our models get, we will never gaze upon the universe with perfect clarity. The cosmos is veiled by design. This faint, universal haze is not a bug in the system. It is a feature of reality. For every distant quasar whose light we capture, there are countless others whose light was completely extinguished by a dense galaxy in the foreground, a thick filament of the cosmic web, or the simple, cumulative absorption across an unimaginable void. These objects are not just dim, they are permanently, irrevocably hidden from our view. They exist in regions of space-time from which no information can ever reach us. Science operates on the principle of observation, but what happens when the universe itself dictates that some observations are forever impossible? This opacity forces a profound philosophical shift. We are not building a complete map of the cosmos. We are piecing together a portrait from the light that managed to slip through the cracks. Our entire history of the universe, from the first stars to the great reionization, is a story told by the survivors, the photons that won a billion-year-long lottery of avoidance. The rest, the lost light, carries tales we will never hear. Yet, within this limitation lies a strange and beautiful clue. The opacity is not random noise, it is structured information. The very pattern of the shadows, the specific way the light is filtered and dimmed, encodes the history of everything it passed through. The faint reddening whispers of intergalactic dust, the deep troughs shout of primordial hydrogen, the subtle scattering hints at a sea of hot plasma. The fog itself is the message. By studying what we cannot see clearly, by meticulously decoding the imperfections in our vision, we are learning more about the universe than if it were a perfectly clear pane of glass. A flawless window shows you what is on the other side, but tells you nothing about the space between. Our murky, imperfect window reveals the intricate structure of the medium itself, the cosmic web, the history of star formation, the evolution of galaxies, and the behavior of dark energy. So, is the universe ultimately knowable? Perhaps not in its entirety. There will always be realms shrouded in permanent twilight. But the ultimate mystery woven into reality is this: the very act of veiling reveals. The cosmos hides its deepest secrets not behind a wall, but within a gentle, luminous mist. Our quest is not to eliminate the fog, but to learn its language, to understand that in the delicate interplay of light and shadow, the universe is telling us its most complete story. Our journey through the cosmic veil has taken us from the faintest whispers of missing light to the grand architecture of reality itself. We began with a simple, unsettling observation that the universe is not perfectly clear. From that single crack in the window, we followed the trail of clues into a labyrinth of 25 interconnected mysteries. We tracked missing photons through a ghostly forest of absorption lines, confronted the profound shadow of the Gunn-Peterson trough, and debated whether the haze was spun from primordial atoms or the dust of dead stars. We mapped the cosmic web's clumpy geography, audited the universe's insufficient energy budget, and questioned whether the first galaxies could hold onto their light. We encountered galactic roadblocks in damped systems, listened for the hum of the ultraviolet background, and witnessed the delayed clearing of helium by brilliant quasars. We searched for the searing plasma of the missing baryons and grappled with the dual nature of black holes as both searchlights and shadows. We tried to draw the timeline of transparency, only to find our date a point sparse and our cosmic clocks slightly out of sync. We built digital universes on supercomputers, their outcomes hinging on recipes for physics we cannot see, and we even dared to question if the fundamental constants themselves might be shifting. Finally, we saw how this entire quest is entangled with the greatest tensions in cosmology, like the Hubble disagreement, and how our future vision depends on the fleeting flashes of gamma-ray bursts. This is the cosmic opacity problem in its full, magnificent scope. It is not one puzzle to be solved with a single equation, but a vast, living web of questions. Each mystery pulls on the others, a reminder that in cosmology, you cannot touch one thread without making the entire tapestry tremble. This interconnectedness is not a flaw, it is the engine of discovery. Every mismatch between prediction and observation, every faint tension in the data, is a signpost pointing toward a deeper truth we have not yet grasped. It tells us our map of reality is incomplete, and that is the most exciting place for science to be. The story of the universal fog is still being written. New telescopes will peer deeper, new simulations will grow more precise, and new theorists will propose ideas we cannot yet conceive. The answers to these 25 mysteries will redefine our place in the cosmos, revealing not just what lies in the darkness between the stars, but the very nature of the light that connects us to it all. Which layer of this cosmic enigma captivated you the most? Was it the haunting forest of missing light, the frantic search for the first photons, or the philosophical limit of a universe that forever hides part of itself? Let us know in the comments and subscribe to join us as we continue exploring space's greatest unanswered questions. The next discovery is waiting just beyond the veil.